Alright, so what I want to do today is I want to cover some of the material from Chapter 2. I don't want to go through all the different steps, I can trust that you can read that. So I told you for the first week of class that you were supposed to have read through page 53 or 55. We haven't quite gotten there in the lectures right now. You should be reading ahead and building up a huge strategic reserve. Life happens. When you get older and you have kids, life happens to them, which then propagates to you. Build up as much of a reserve as you can in the reading. Try to get at least a chapter ahead of me so that you have stuff in the bank so that when things happen, you have extra space. Alright, so the game plan for today is I want to start off with Russell's paradox. So there are a lot of reasons to discuss Russell's paradox in a probability class. The first is, this is a 300 level math class. We are trying to do things rigorously. At the same time, we are not requiring you to take mathematical analysis, which is exactly what we need, real analysis, to do all this rigorously. So we're kind of being pulled in two different directions. Right? So now, what can we do? Option A, everybody read real analysis tonight. Okay? Or talk to your friends who've already read real analysis. And then we will have the language to do things properly. So we need the language of open sets, closed sets, a lot of the notions of convergence. Towards the end of the semester, if possible, I want to try to get into some of the convergence theorems. Okay? Failing that, instead, what we'll do is we'll try to just highlight a few of the key ideas, a few of the key places where some of this stuff comes in, as well as a need as to why you have to be careful. So my brother has a degree in electrical engineering. He now works at MathWorks. He doesn't understand at times why we mathematicians obsess so much over things that don't really show up in the real world. You worry about all these functions that have these pathological properties. All the functions they look at, they're always nice functions. The reason we care so much about these is every now and then you do encounter one of these. And when you're trying to do the general theory, you have to be able to handle these cases. So Russell's paradox is going to serve two purposes for us. The first is just as a warning about how careful you have to be when you build up your axiomatic system. The second is, for probability, it's going to teach us, related to similar paradoxes, that we cannot assign probabilities to arbitrary events. It's not Russell's paradox that will cause problems, it's something else. It's the axiom of choice and the Banach-Tarski paradox. But what this means is you cannot assign probabilities to every possible event. Fortunately, the events we want to assign probabilities to, for the most part, are accessible. For the most part, we can assign probabilities to events. Okay? The ones we care about, that's not going to be a problem. All right. The way Russell's paradox works is, let P of x be x has property P. Anybody have any idea what property P might be? Yes?
It's an odd number.
X is an odd number. Wonderful. Anything else for property P?
Degree 2, 3.
X is a polynomial of degree 2? Absolutely. We can use X to represent a polynomial. It could be, yes.
It's a prime factor of 2 greater than 1,000.
Prime factor of 2 greater than 1,000. I'm not going to find too many of them, which is absolutely fine. Okay? So the idea is, let's consider some property, and let's let P of x be true if x has the property and false otherwise. Let's let R be the set of all x such that P of x is true. What we're doing is we're collecting all the objects in the universe that satisfy property P. And the reason I love this example is because it's so easy to write this down, and if it's the first time you've seen it, not to be aware of what you're doing. We've made a major assumption. The assumption we've made is we can gather all objects with a given property and call that a set. Now, most of you, unfortunately, have not taken a class in set theory. Once in your life, you should see the real numbers constructed axiomatically and rigorously from the beginning. Once. That's more than enough. Okay? It's a lot of work to do this correctly. And unfortunately, a lot of our intuitions are wrong. This example, who do you think is due? Who do you think this example is due to? Russell. I believe he found this when he was a grad student, and he presented it to basically one of the giants of set theory who was working on the treatise of set theory. And since this is being recorded, I will not use the correct language that was said when this example was brought to his attention, as they realized the entire axiomatic system came crashing down. This is not a set. Here's a very simple way to try to figure out if it's a set. If R is a set, let's see if X is in R. What are the two possibilities?
X is in R.
X is in R.
And then
So case 1, X is in R, and case 2, X is not in R. Well, if X is in R, R is the collection of all objects, such as P. Oh, sorry. I have to tell you what P is going to be. And so for R, such that X, that's going to be the special choice of P. The special choice of P of X. X is an element of X. Okay? So there's many different choices. We gave a couple of different choices. I forgot to write this one down. Can you give me an example of an X that is not an element of itself?
Empty set.
Yes, the empty set is not an element of the empty set because the empty set has no elements. Good. The set of positive integers. Is the set of positive integers a positive integer? No. There's levels of hierarchy. And so most things are not elements of themselves. So let's look at the collection of all objects that are elements of themselves. Will X be in X? Will X be in R?
Well, if R is X, then yes.
So case 1, so we're assuming X is in R, so then the answer would be yes. And in case 2 we said X is not in R, would that be consistent? So R is the collection of all things that are elements of themselves. And I'm telling you X is not in R. Is this consistent?
No.
So if X is not in R, X can't be an element of itself. So I think that this would also be consistent. So I'm deliberately tweaking things from the book. What am I doing differently?
You said X is an element
I
of
said
X.
X is an element of R. I'm sorry, X is an element of X. What's Russell's paradox? X is not an element of itself. It's amazing what a difference that does. Let's imagine all the things that are not elements of themselves. So now we have the situation where X is in R. R is the collection of all things that are not elements of themselves. What does it mean for X to be in R? So what does it mean now?
If X is in R, then X is not an element of X.
So since X is in R, this implies X is not in R. So it makes a huge difference which property you take. This is a strange property to take, not being an element of itself.
Wait, no, X is not in X.
Okay, so since X is in R, this means, means X is not an element of X. But R is all items that are not elements of selves. So we get X is in R. Where's the contradiction? Let's screw this up. Alright. X is not an element of X. Case 1, X is in R. So if X is in R, the only way X can be in R is if X is not an element of itself. And what was there? No, now I've successfully confused myself, and I apologize. Do we want it as an element or not as an element? Yes.
In the book, it was not as an element, but the question is R in R?
Oh, it's R and R. Oh, thank you. That's what I'm doing wrong. I did want that to confuse you, but I'm writing X by mistake. Thank you. Is R and R. Thank you. That's where I'm doing it wrong. Thank you. All right, take 3. All right. I did want to confuse you by doing X as an element of X. I then unfortunately confused myself. All right, so is R a set? We want to see if R is in R. Thank you. So there are 2 possibilities. R is in R, and R is not in R. What we're doing is we're taking a special choice of X. All right. So, while unfortunately this has now been preserved for posterity, it's actually not bad to see how easy it is to get confused. All right. This is the importance of having good notation. X is an arbitrary element. So what we got at the end is, which element of X are we looking at? There are many elements of X. There are many choices of X we can look at. What is the natural one to look at for this problem? Either we know a priori a specific element that is not an element of itself, or the only thing we've really created is this new set R, and it's worth thinking about this new set R. So again, this was sadly not deliberate. I did not mean to make this mistake, but having made this mistake, let's make the most of it. When you have a problem like this, what do we have in play? The only thing we've really added is this new set, or this new collection, I really shouldn't call it a set, this new collection R. And so let's ask ourselves, what can we say about R? What can we explore? Well, the most natural thing is to check R relative to this property. Is R an element of R? Or is R not an element of R? What would it mean for R to be an element of R? R is the collection of all things that are not elements of themselves. So the only possibility is what? If R is in R, by definition, R is not in R. So, contradiction, case 1 doesn't happen. Normally we would say, good, we don't even have to check case 2. These 2 cases are mutually exclusive. Case 1 doesn't happen, case 2 must happen, and therefore R is not an element of R. Given that I have screwed up this lecture so badly up until this point, you should not trust me on anything. And let's just go through case 2 just to make sure. Well, let's assume R is not an R. By definition, if R is not an R, then what is true? R is an R. R is the collection of all things that are not elements of themselves. So, by definition, if R is not an R, then R is an element of R. We are in the ridiculous situation where R is an element of R if and only if R is not an element of R. What's the only thing we can conclude? We must have made a mistake somewhere. Where was the mistake? The mistake was assuming that this was a set and that this was something we can talk about. This is not. Now, if you think about it, this is normally not the way you would want to use the relation element of. We're comparing 2 things of the same level. We're comparing, is the set of natural numbers a natural number? And so in that situation, this is a little bit unusual to have a comparison like this. And so there's versions of set theory now that handle situations like this. But essentially, what happens is we have to be extremely careful in terms of what we call a set. There is really only one set we know. Anybody know the one set we know? The empty set. Technically, that is the only set we understand. Okay? Can somebody enumerate all the elements of the empty set? Thank you. Okay. Excellent job. Right? There is nothing in the empty set. So as a quick aside, I'm going to just quickly show you how you build things with the empty set. All right. Can anybody create a set using the empty set now?
Set of the empty set.
The set containing the empty set. Can anybody build a new set? The set containing...
The set containing the empty set union with the set containing the empty set.
And now the next set I could form is the empty set, the set containing the empty set, and the set containing the empty set, and the set containing the empty set. Anybody want to assign a nice label to this? If you were thinking of numbers, what number would you assign to this? 0. 1. This has 3 elements. Less than becomes inclusion. 3 contains 2, 1, and 0 as subsets. This is one way to build the integers. Okay, starting with nothing, literally. Okay? This is not what you want to do in a probability class. Okay? I want to show you a little bit of what needs to be done if you want to really work with things rigorously. What we know is we know the empty set, and we can build up from the empty set. All right. The other reason I want to get to this point is to talk a little bit about sizes of sets. If I give you something like this, what is the size of this set? 3. And in fact, that's why we're going to call it 3. Now, there's lots of different sets that have 3 elements. And so the question is, maybe in some sense they're all equivalent. If I have anything with 3 elements, I can kind of come up with a mapping from one set to the other. And this is how we talk about comparisons of sets. You know, I'll have some kind of reassignments. Okay? So can somebody give me 2 different sets that have the same number of elements? Finite. 2 sets with the same finite number of elements. Yes?
The set containing 1, 2, 3, and
Okay.
the set containing 4, 5, 6.
The set containing 1, 2, 3, and the set containing 4, 5, 6. So we have 1, 2, 3 here, and we have 4, 5, 6 here. So we can have a one-to-one onto map that takes an element here and associates a unique element here, and vice versa. How many different maps do we have? How many different ways can I map the 3 elements to the 3 elements so that each element gets mapped to one and only one element? 6. I have 6 different ways. 1 can go to 4, 5, or 6. Once I choose where 1 goes, 2 can go to the 2 remaining, 3 can go to the remaining. I have 6 different maps. For a lot of purposes, I don't care which map. I'm just trying to show the sets have the same cardinality. Okay? So this is finite sets. For finite sets, we can just enumerate them and we can compare one at a time. With infinite sets, it's much trickier. There becomes this notion of sizes of infinity. And so this leads to the notions of countable, the lowest possible infinity, and uncountable, which is a significantly larger one. This leads to power sets and all that stuff. For the most part, we are not going to work with uncountable sets, primarily because everything collapses in terms of what goes on with uncountable sets. We can't deal with that. Countable sets, the quickest way to think about this is there is a way to go through your system and you know when you will hit any given object. With uncountable, we don't necessarily know when we'll do that. So the idea is, so now we'll do cardinalities. So we say a set is countable if there is a one-to-one and onto map, bless you, from it to the natural numbers. And if you want, you can include 0 or not include 0 in the natural numbers. It doesn't really matter. So another way of looking at this is, here's our set S. Its elements would be S1, S2, S3, S4. There's a nice way to enumerate all of them. Are there more even numbers or positive integers?
The same amount of both.
There's the same amount of both. Anybody want to give me another answer? I'll accept the other side as well. Anybody want to say that there's more?
Well, I mean, they're both infinities, right?
They're both
But it's
infinities.
just the relative size of the infinities, which is
Well, they're both countable.
They're both countable. So if I want to look at the set of even numbers, we have 2, 4, 6, 8, well, 8, 10. Then we have a very nice map. N goes to 2n. There's a one-to-one correspondence between positive integers and even numbers. They have the same level of infinity. Okay? In another sense, however, there's more even numbers. So if you look at integers less than or equal to x and evens less than or equal to x, and you divide by x, this gives you the percent of numbers at most x that are integers, the percent of numbers at most x that are evens. What fraction will this be?
50.
About 50%. Maybe slightly off if I stop at an odd number or an even number, but and what will this be? What fraction?
100.
100%. This is a major idea. We're going to see this throughout the semester. Depending on your choice of metric, you can get different answers. If I want to just go by a percentage, there's more even numbers than integers. Okay? Don't forget the basics you've learned all the way going back to high school and earlier. You know that your intuition, there's a lot more integers than even numbers. Yes. Okay? But in the sense of cardinality, they're both infinite sets and they're both the same level of infinity. Yes.
Why is there more even numbers than integers?
No, there's not more. There's not more.
Well,
even.
in the second case there.
This one?
Yeah.
Well, there's only 50% of the numbers are even. If I look up to
There are
x,
more integers than even numbers in
there are more
You
integers
said-
than
you
even
said
numbers
the
in this view. Yes.
Oh, okay. Yeah. Sorry, you said
Yes.
the opposite.
Oh, did I say the opposite? Okay. It's been a tough few days. I apologize. 50% of all the numbers up to a given height are even. 100% of all the integers up to a given height
Right.
are integers.
Yeah.
And so if we look at it that way,
Like what percentage would you give to the rationals?
so then you've got to be careful because now the rationals are filling things in.
Yeah.
And so one thing you can do is you can look at rationals with a given denominator. And say maybe I want to look at all the numbers from 0 to 1 with the given. That becomes a little bit harder in terms of dealing.
Wait, then hold on. If that case, the second case that you drew up, there are more integers than even numbers, you could just assign any value to x, right? So if it gets as close to infinity as possible. then
Because
there's still
we're asking different questions. I'm asking what fraction of the time am I hitting an integer as I go up to a certain height? 50% of the time I'm hitting an integer. I mean, an even integer, 100% of the time with my integers.
Right. Okay.
But the two sets are the same. If you want, instead of looking at even numbers, I could look at numbers that are multiples of 3. Are there more multiples of 3 or more integers?
So as long as it's finite.
I'm sorry?
As long as it's finite, right?
As long as I do a finite count and I look at the percentage will be different. The relative covering of the interval up to x will be different, but they will both have infinitely many elements. They're separated. That's one of the things that makes the subject so important. It's not a continuum of events, it's a separated sequence. If you want a continuum, and again, I am thrilled to have discussions like this rather than defining everything. Let's take the interval 0, 1, and now, let's see if I can do this right. I'm going to draw a 45-degree angle over here and make a right triangle. Are there more? Which segment is longer? The diagonal or the horizontal? the diagonal. But there's a one-to-one correspondence between every element on the horizontal and the diagonal. So they have the same number of elements, but the length is different. It's just arranged in a very different way. As soon as you start to deal with infinities, life is strange. And you've got to be very careful how you deal with infinities. There is a one-to-one correspondence between these two sets. So as sets, they have the same number of elements. But the way they're somehow packed together, one of them has a longer length than the other. If you want, you could actually even do this again and do it one more time. And now draw a 45-degree angle here and project downward. So now this point would come back like over here. And what I've now effectively done is I've doubled the interval. And so I've gone from the interval maybe 0, 1 to maybe minus 1, 2. You know, essentially just multiply everything by 2. This is very similar to the notion of evenness. Okay? So just as notation, we use aleph naught to represent the size of the natural numbers or the integers or the rationals. These all have the same cardinality. We use, and we're not going to really use it much in class, aleph 1 for the size of the reals. And a big question in mathematics is there any set that is strictly larger in cardinality than the rationals and strictly smaller in cardinality than the reals? And this is called the continuum hypothesis, and the answer is, it's up to you. If mathematics is consistent, then if you add the existence of a set of size strictly between, mathematics will still be consistent. If you say there is no such set, it will also be consistent. The person who put the final nail in this was one of my mathematical grandfathers, Paul Cohen. And so, in terms of what happens with sizes of sets, things get strange. The reason I want to talk about this is to really hammer in, we've got to be careful when we talk about probabilities of events. What events are we talking about? For the most part, we're going to be talking about open intervals, closed intervals, singleton points, unions of these, countable unions, countable intersections. These are the key building blocks that we're going to work with. We have to be very, very careful about, in general, what sets. So section 2.6 in the book talks a little bit more about sigma algebras. This is where you get into measure theory. This is how you make all of this rigorous and legal. Okay? As an aside, this actually leads to the longest song in the English language. Anybody know the song? Aleph naught bottles of beer on the wall. All right, so I'll let you figure out how you would sing that song. So, 3. Warnings about infinities. A reasonable working definition of a mathematician is somebody who is careful with infinities. Right? That at least covers a lot of the branches of analysis. Is we worry about doing things with the infinite, because depending on how you do things, things can go wrong. And they can go wrong in very bad ways. So what I want to do is I want to risk recalling a result from multivariable calculus. I know at least some of you took multivariable calculus with me, so I'm pretty sure I did that with you guys. For those of you who did not take multivariable calculus with me, I'll just restate it right now. How many people remember Fubini's theorem? It's one of our two main techniques for doing integration in multivariable. What's Fubini's theorem?
Is that where you nest the integrals
Okay, and what does Fubini allow you to do?
to take them separately?
Not quite take them separately.
In succession.
Not quite. You're close. What is Fubini? So Fubini, let's take an integral x goes from a to b, y goes from c to d. We'll take a nice rectangular region, f of x, y, dy, dx. What will Fubini tell us about this?
Can you multiply them?
What do you mean by
next to each other?
multiply?
Well, you split fxy apart, and you.
Well, most of the time f of x, y won't be splittable.
Okay.
Reverse the order of integration.
Yes. In many cases, this is the same as y goes from c to d, integral x goes from a to b, f of xy dx dy. This is one of the major techniques in multivariable calculus, switching the order of integration. It is not always possible to switch the order of integration. So if you took a good class, they should have at least warned you about what conditions do you need to do this. And again, most of you are not going to use most of the material in this course for most of your life. What I want you to be aware of is what's out there, what can be done so that if you're in a situation where you need any of this, it's there. And I want you to be aware of how easy it is to make mistakes. This kind of builds back to the Russell paradox. It's very easy to subtly assume something. You cannot always switch the orders of integration. If the integral of the absolute value is finite, can switch. Can switch if the integral of f of xy in absolute value, I'll call it dA, is finite. So if that integral is finite, you can switch orders. If that integral is not finite, you may or may not be able to switch orders. What I want to do is I want to give you an example where Fubini's theorem, where the conclusion of Fubini's theorem fails, where you cannot switch the orders of integration. And again, I want to do this to really hammer home the point of why we have to spend so much time in this class proving things. Because statements that you think would be intuitively plausible sometimes fail. Okay, rather than doing things with integrals, I'm going to do a slightly easier version. I'm going to do things involving sums. So I'm going to do a double sum. I'm going to show the sum n goes from 0 to infinity, the sum n goes from 0 to infinity of a mn is not always equal to the sum n goes from 0 to infinity, the sum n goes from 0 to infinity of a mn. That sometimes the order in which you do things matters. Now, if you think about it, I'm adding the same terms. I'm just grouping them in a different way. Depending on how you group things, you can get very different results. Okay? So let's do the following example. I'm going to draw a bunch of dots. So this is the point 0, 0, 1, 0, 2, 0, 3, 0, and so on. And I'm going to tell you in a moment how I'm going to define my sequence at these points. Alright, so I'm going to define my sequence to be plus 1 here, minus 1 here, and then 0 for the rest of eternity as I go up. In the second column, I'm going to go 0, plus 1, minus 1, and then 0 for all eternity. In the next column, I'm going to go 0, 0, plus 1, minus 1, and then 0 for all eternity. So hopefully the pattern is clear. There are two ways I can sum this. I can fix a column, sum the column, and then vary my columns. Or I can fix a row, sum in the row, and then vary the rows. Which would you like to do first, rows or columns? Columns, why?
All the same.
They're all the same, right? If there's two options and one of them is easier, do the easier one. If I fix a column, doesn't matter which column, in each column I have 1 plus 1, I have 1 minus 1, and the rest are 0. Each column sums to
0.
And now when I sum over all the columns I get, alright, so here, n stands for, is it row or column?
Column.
Row.
So who just took linear algebra? So when you write your matrix, you write it as A11, A12, A13, right? And then A21, A22. So normally the first number, is this how you normally write your matrices? So when we're writing it like this, does everyone write their matrices like this? How do people write their matrices?
As squares. Just like with all the...
Just,
Well, no, I'm saying when you're filling in the entries,
yeah.
is this how you would write them?
It's row column, right?
Yeah, that's right.
Yeah.
Does everybody write their matrices like this? I want to make sure we're all on the same page. Yes, we're all writing them like this. Alright? So over here, is this the first row or the first column for this entry? First row. So the first index is referring to our row, and then the second index should be referring to the column. Fortunately for this problem, it doesn't really matter. We can write the following. Sum over columns, then rows, and that will give us sum over rows, then columns. So now if we sum over rows, what's the sum over the first row? Second row, third row. And so if we do it that way, we get 1. 0 does not equal 1. What this tells us is we have to be careful. We can't just interchange the order of sums. So Fubini's theorem from calculus, there are some real conditions that are lurking if we want to be able to make these arguments. Yes?
Don't you eventually at the, like, towards infinity, isn't there another -1 at the end, or do you?
But the thing is, it goes off to infinity. So there is never a row beyond the first one that doesn't sum to 0. This is the difference between countables and uncountables. If I go to the 2 billionth row, then I will have a -1 and then a +1. I'll have a lot of zeros first, then a -1, then a +1. No matter what row you give me, if it's not that first row, it will sum to -1. It will be a -1 followed by a 1, and it will sum to 0. So these are warnings about why we have to be so careful in forming definitions of probabilities and asking which elements can we assign probabilities to. One of the dangers in a class like this is you have a lot of intuition. You've been working with probabilities all your life. Most of the time your intuition is correct. One of the funniest quotes in any textbook I've ever read was one of my high school physics books, which was trying to describe special relativity to, I think, 10th graders. And it said, these results may seem counterintuitive, but you have to remember most people don't have experience traveling at 3/4 the speed of light. And, of course, yes, none of us, are traveling at 3/4 the speed of light. It's very natural to take a situation you know and extrapolate it to other situations. And so you can take the situation of looking at small velocities and say the patterns I observe here will continue to persist in other regions as well. And so one of the big things you see is speed appears to be additive. If I'm on a train that's traveling at 100 miles per hour and I'm running in the same direction at 30 miles per hour on the train, I'm on drugs or something, then it looks like I'm going at 130 miles per hour relative to somebody on the ground. Right? If I ran in the other direction that the train was going, how fast would it look like relative to somebody on the ground? 70. It turns out it's not exactly 70, it's not exactly 130. There are small corrections. They're in like the 8th decimal place. The machines, the measurements we're taking are not accurate enough to see that. And so it looks like velocity is additive. And people extrapolate that further on. If you need a good quote, Mark Twain is a wonderful person to look to. One of my favorite quotes of his is, "A cat that jumps on a lit stove will not jump on a lit stove again, but will not jump on a cold one either. For each lesson in life, take only the lesson you're supposed to learn from it." And so here, when we're looking at physics with small velocities, it is wrong to say that this extrapolates to arbitrary speeds. And there are a lot of issues that happen there. So you have a lot of intuition with probability. This is both a blessing and a curse for this class. You have some rough idea of what's going on. If I have independent events, the probability that they both happen should be the product of their probabilities. You have some wonderful intuitions. The problem is there will also be a couple of situations where your intuition will mislead you. And you've got to be careful. You always want to be asking yourself, am I subtly assuming something? One of my favorite things from high school geometry classes was splitting, I don't know if anybody still does this, the paper into 2 columns, statement and reason. Every time you write down a statement, you have to give a reason. Because I said so, because I outrank you, these are not valid reasons. You have to give a mathematically accurate reason. It follows from the definition, it follows from this theorem, it follows from this lemma. So this is a habit you really have to get into, is be very cautious about what you're doing and why you're doing it. Okay, so now what we want to do is we want to move on to section 2.3. So this is now, I think, events. Okay, outcome spaces, events. Okay, so we have a lot of notion here. So the outcome space or the sample space, this is the possible candidates, the events, these are the elements. And we can assign probabilities, which we'll do later, to the elements of the space. And then we can look at maybe unions of elements of the space to form other objects and talk about the probabilities of these. And what we want to do is we want to have a wish list of things, right? So if you have some space omega and you have an event A, what would you love to be true?
The probability to just be number A over
Okay, so one thing, that's a special probability measure. That's the uniform probability measure that says the probability that A occurs is the number of elements in A divided by the total number. What would be a good wish list thing to hope for the probability of A?
That it's in space, omega.
Okay, so one is that we can talk about the probability of A. Right now, this is a wish list. So for my wish list, I'm going to assume I can talk about everything. What would we like for the outcome?
equal 1, probability to be 1.
I mean, this could be the probability that the Giants beat the Patriots. I don't want that to be 1.
It's easier if it is.
For some people. What do I want probabilities of events to be?
Between 0 and 1.
Between 0 and 1. So that seems like a reasonable start. I want 0 to be less than equal to the probability of A to be less than equal to 1. That's a great initial wish list. Another wish list might be if, say, AI is a, let's say the pairwise disjoint. So this means AI intersection AJ is empty if I does not equal J, then the probability of the union of the AIs, what would you wish that to be?
1.
Can't have everything be 1. Again, these could be all the probabilities of all of the Patriots' opponents winning the Super Bowl. I don't want that to be 1.
Just the sum of the probability of the
It should be the sum of the probabilities of the AIs. The probability of the union should be the sum of the probabilities. One of your homework problems was the derivative of product. What is your wish? If you could have written the laws of calculus, what would you have the derivative of FG be?
The derivative of both of them multiplied.
Yes! That would be much better. What would be the derivative of the quotient? It would be the quotient of the derivatives. Yes, my job is to crush all your wishes. Right? That is not going to hold. Turns out this too does not hold either. It is too much to ask that the probability of a union is the sum of the probabilities. And what this tells us is we've got to be very careful about how we build up our notion of probability. This seems quite reasonable. The difficulty is, what kind of union are we taking? Are we taking a countable or an uncountable? And so I'm not going to go into great detail. I'll just say quickly why 2 is bad. Let's let omega be the interval 0, 1. Let's let a sub x be the point x. Then omega is the union over all x in 0, 1 of ax. It's the union of all these singletons. If the probability of the union is the sum of the probabilities, then the probability of 0, 1 is the same as the sum of all these probabilities. If I put on this kind of uniform measure that you were talking about a few moments ago, what's the only value I can put on here? It's got to be the same for all of these xi's, for all these ax's. If I put in a positive number, this will become a plus infinity. If I put in 0, this will become 0. And this union is all of 0, 1. So the problem is, if I try to break up 0, 1 into an uncountable union, because there's uncountably many real numbers, there is no consistent way to assign probability if I want all the probabilities to be equivalent, which is a very natural thing that I want to do. I want to have all events equally likely. This has some very strange repercussions. So one of the examples is, well, let's talk about, everybody has some notion of what it means to draw an element uniformly or randomly. One of my favorite court cases a couple of years ago is there was a raffle for green cards to enter the United States, and they were supposed to select people randomly. When you hear people being selected randomly, you also add another assumption in your mind. What other assumption are you adding? It's not just random. What kind of random?
They must have like pre-selected a pool of people.
Well,
randomly chosen.
they did in some sense do that. You would implicitly assume that everybody has the same chance, that it's fair, that no person or no group of people have a better chance of being chosen. That when I say I'm choosing people randomly, I mean I'm choosing people uniformly. Every person has the same probability. It turns out they only drew names from the people who applied in the first 2 days of the month. This is like, spell a little computer whoopsie. It was still random. They chose randomly from everybody who applied in the first 2 days, but it was not uniform. And there was a court case as to was this a legal way to be giving these visas. We often have notions. So here I want to talk about choosing an element uniformly at random. I want all points to be equally likely. If I choose a number, if I choose a random real number, I've got to choose something. What's the probability I choose any specific number? Well, if they're all equal, the only thing I can assign is 0. So that means I can't choose anything. Now this is absurd. I've got to be able to choose something. If I'm choosing a number at random, I've got to choose something. So I'm going to end the day with the following. How do we get around this? 1, there is no such thing as choosing a random real number uniformly from 0, 1. I can only work on a computer. I can only do finitely many operations on zeros and ones. I can only access a small subset of the rationals. And that's the best way to look at what we're doing, is we're not really choosing anything at random. The other way people like to say is, if you keep doing this process, the probability you ever choose any number twice is 0. I don't like that as much. What I prefer instead is if I want to choose a number randomly in 0, 1, if I choose any subinterval AB, what's the probability my number lands in AB? What should that be if I'm choosing things at random uniformly? What, the class is ending, we gotta say it fast. It should be B minus A. The probability I lie in any subinterval should be B minus A. So we'll continue with this on next time. This is the way around it. These are the events we can talk about. The probability you're in a certain interval of a given size. That makes sense. The probability you're a specific singleton, that doesn't. So this was a bit of a technical lecture, deliberately so that we have things on a firm grasp.